Understanding JVM Memory Model, Java memory management are very important if you want to understand the working of Java garbage collection. This is Balaji. Today we will look into memory management in Java, different parts of JVM memory and how to monitor and perform garbage collection tuning. The Java Virtual Machine, JVM, provides two major services for any Java application: memory management, and running the compiled bytecodes. Much of the memory management is done by the garbage collector, and the compiled bytecodes are run by the HotSpot compiler. JVM defines various runtime data area which are used during execution of a program. Some of the areas are created by the JVM whereas some are created by the threads that are used in a program. However, the memory area created by JVM is destroyed only when the JVM exits. The data areas of thread are created during instantiation and destroyed when the thread exits. JVM memory structure is divided into multiple memory area like heap area, stack area, method area, native method stack and PC registers. The heap area is the memory region where objects are allocated. The heap is the main area of memory used by the JVM to store objects and their associated data. The heap is where most of the dynamic memory allocation occurs in Java. It is shared among all threads and is created at the start of the application. Examples of objects that are stored on the heap include instances of classes, arrays, and objects created using the new keyword. The heap is divided into generations, such as the young generation and the old generation, to optimize garbage collection. Young generation is further divided into Eden space and the two survivor spaces S1 and S2. The young generation, Eden space, is where newly created objects are initially stored. When the Eden space becomes full, a process called a minor GC, garbage collection, is performed. During this process, the JVM moves all live objects from the Eden space to one of the survivor spaces. The objects that are not moved to the survivor spaces are garbage collected. The survivor spaces are used to store objects that have survived one GC but not yet moved to the old generation. The old generation or the tenured space is where long-lived objects are eventually moved to. Objects that have survived multiple minor GCs are promoted to the old generation. The old generation is subject to a full GC, which is a more expensive process than the minor GC. The JVM uses different algorithms and tuning parameters to manage the young generation and old generation. The goal is to provide a balance between GC efficiency and application performance. The heap size can be controlled using XMX and XMS arguments while starting the JVM. The method area, also known as the metaspace in newer versions of Java starting from Java 8, replacing the permanent generation permgen, is a part of the JVM memory. It is shared among all threads and is typically allocated at JVM startup. It stores class-level information, including the bytecode of loaded classes, field and method data, constant pool, string pool, and other reflective information. The string pool in Java, which is a special area of memory that stores string literals. It is a part of the JVM's method area. Metaspace is a memory region in Java that stores static information pertaining to a Java application, including metadata associated with loaded classes. Unlike its predecessor, permgen, metaspace does not have an explicit size limit by default and expands dynamically. However, without an explicit boundary set, the metaspace size is implicitly restricted by the available system memory on the hosting machine. Each thread in a Java program has its own stack, which is used for tracking method invocations and managing local variables. The stack operates on a last-in first-out, LIFO, principle. The stack memory is used to store method frames, which contain information about method parameters, local variables, and intermediate results. The stack is a memory area used to store the execution context of a thread. Each thread has its own stack, which contains information such as the current method call, local variables, and the address of the instruction currently being executed. When a method is called, a new frame is created on the stack to store the method's parameters and local variables. When the method completes, its frame is removed from the stack. The term PC registers typically refers to the program counter registers, which are part of the Java Virtual Machine, JVM, architecture. The program counter registers are responsible for keeping track of the current execution point within the bytecode of a method being executed. Each thread has a PC register, which holds the address of the currently executing instruction. The PC registers are used to point to the next bytecode instruction to be executed by the JVM. The non-native method has a PC which stores the address of the available JVM instruction, whereas in a native method, the value of program counter is undefined. When a thread starts executing a method, its PC register points to the first bytecode instruction of that method. As the thread executes each bytecode instruction sequentially, the PC register is incremented to point to the next instruction. Branching instructions, such as conditional jumps and method invocations, cause the PC register to be updated accordingly to redirect the flow of execution. In the event of an exception being thrown during the execution of a method, the PC register is used to determine the appropriate exception handler. PC registers are a fundamental component of the JVM architecture, playing a crucial role in managing the execution flow of Java bytecode instructions within individual threads. The native method stacks are used to support native, non-Java, method calls. They are similar to the Java stacks but are used for executing native code. The native method stack stores the execution context for native methods, which are methods written in a language other than Java. The native method stack operates separately from the Java stack and has its own memory allocation. It's important to note that the impact of the GC and JVM parameters can vary based on your application and JVM version, so experimentation and monitoring are crucial. XMX sets the initial and maximum heap size. XMN is used to adjust the young generation size. XX new ratio is used to adjust the ratio of the young generation to the old generation. XX new size and XX max new size specifies the minimum and maximum size of the Eden segment in the young generation. XX survivor ratio specifies the size ratio between the Eden space and the survivor spaces in the young generation. XX metaspace size and XX max metaspace size are used to set the initial and maximum metaspace size. XX plus use serial GC, XX plus use parallel GC, XX plus use G1 GC parameters are used to choose a garbage collection algorithm. XLog GC parameter is used to enable the garbage collection logging. XX plus heap dump on out of memory error parameter is used to generate the heap dump in case of out of memory error. XX plus print heap at GC parameter is used to print the heap size information at regular intervals. It's important to understand memory management to make sure your Java programs run smoothly and don't waste resources. It's important to note that GC tuning requires careful analysis and experimentation to find the optimal settings for your specific application. Configuring memory and GC parameters in Java involves striking a balance between available system resources, application requirements, and performance goals. It's recommended to monitor and analyze your application's memory usage and GC behavior to make informed decisions about memory configuration and tuning. Monitoring Java memory usage in production environments is crucial for detecting memory leaks, optimizing performance, preventing out-of-memory errors, troubleshooting performance issues, and ensuring the overall stability and reliability of Java applications. By monitoring memory usage effectively, you can proactively manage memory resources, identify potential issues early, and optimize application performance. I have reached the conclusion of this session and look forward to seeing you in my next one. I hope you have enjoyed the video. Don't forget to like, share, and subscribe. Thank you for watching my video.